now.
Hi, my dear students. I hope you have power, or if you don't have it, that you get it back soon. And I hope you're doing well. I sure miss you and sure miss going into school and doing experiments and learning chemistry. If you look, we have posted the remaining work for Chapter 10 before we start the next chapter, which is on reactions and some real aspects of chemistry. I've already presented a couple of examples of problems from section 10.1 and 10.3 for section 10, quantitative aspects of chemistry, but from 10.1 and 10.2. Now I'm doing 10.3. I want to work the problems with you for section 10.3, and that is on percent composition. You know, we've learned percent composition, elemental composition, what percent different elements are present in different compounds. And so we've learned about compounds, ionic covalent compounds, how to name them, how to write them. And you know that, for example, CO2, carbon dioxide, we can name it or give its formula, CO2, has 1 carbon and 2 oxygen atoms. One of the things we always want to know is what percent of a given element is found or present in a compound. If I have an example of some iron ore, what I want to know is how much of that ore do I have to dig up to get a certain amount of iron out of it. So percent composition is a very important concept, and you calculate percents the same way you do in any other system. Mathematically it's identical. The percent is the amount of what you're interested in divided by the total. So if you want the percent of high school graduates in a population, you take the total number of high school graduates and divide that by the total number and multiply by 100 to get percent. So we're going to do that same thing here. We've learned about formulas, how to name them, what they represent, and now we're just attaching some numbers to them. The numbers specifically are related back to the molecular weight, the atomic mass, the elemental atomic mass for each element. Now we're going to combine all the elements' masses within a compound together to find a compound or formula weight for a given substance. So let me see if we can just do this quickly by way of example. Okay, so if you look at your section review homework for 10.3, on question 14, when we start working the problems, I just want to remind you that I am at home. I don't have my Flynn scientific periodic table of the elements. I don't even really have a good, all I can do is Google a periodic table and get this information. But 14 says, what's the percent composition of each of the following? They ask you for the formula, the percent composition of chromium oxide. Actually, this would be chromium 3 oxide. Chromium has a molecular mass of 52 grams per mole. That's the big red number on your Flynn scientific table, of periodic table of the elements. Oxygen has an atomic weight, atomic mass of 16 grams per mole. I know it's 15.999 something after that, but rounded to significant figures for our purposes, it's 16. So that will do for us. And the way I find the molecular mass, the atomic mass of this compound, chromium oxide, is I take 2 chromiums, that's 2 times 52, or 104, and 3 oxygens, that's 3 times 16, or 48, mass them together, or just simply add them together. Chromium oxide's formula molecular weight adds up to 152 grams per mole. So if I want the percent chromium, I have 2 chromiums at 52 and I divide that by 152. That's 104 divided by 152, and that is equal to, and this is your answer. If you work it out, it's 0.648, but multiply it by 100% to get percent, and it's 64.8%. Your answer. The percent oxygen in this compound, oxygen has a molar mass of 16. There's 3 in the formula, so 3 times 16 divided by 152, divided by the total mass of the entire compound. So, you know, this is a legitimate test question in itself. What is the formula weight, the formula mass of chromium 3 oxide? And you add up the individual atomic masses for all the elements, multiplied by the number of elements and the subscript, and you get a formula or compound molecular mass. Anyway, if I continue to work this out, this would be 3 times 16 is 48, divided by 152 times 100%. The fraction would be 0.316, but if we write that as a percent, it would be 31.6%. The second one asks for this, I don't know what that is. That might be manganese diphosphate, I think is the name of that polyatomic ion. But it's a compound, Mn2P2O7. 2 manganese, 2 phosphoruses, and 7 oxygens. And if you do the math, 2 times 55, 2 times 31, and 7 times 16, your formula weight for this compound, Mn2P2O7, is equal to, and what did I do? 284 grams per mole. Now, previously, you know, when we were talking about oxygen at 16, that big red number, we called it its atomic mass. And I told you don't worry so much about the units. We give it a made-up unit if we were measuring a single atom of oxygen. We called it 16 or 15.999 something. AMUs, atomic mass units. And we just kind of, I won't say arbitrarily, but we define that as atomic mass unit as 1/12 of the mass of a carbon-12 atom. So, but I said these numbers are going to have much more meaning later, and here's the meaning. Because we never work with a single atom. But I might work with a mole of oxygen, and if I have a mole of oxygen, it's going to weigh 16 grams per mole. A mole of oxygen atoms. If I have a mole, of course it's O2 in the atmosphere, so if I have a mole of oxygen molecules, it would be 2 times 16, or 32 grams per mole. That's a measurable amount. In fact, that would be a volume of oxygen about this big, 22 liters, 22.4 liters. So, here, if I want the manganese, percent manganese, that's Mn, please don't confuse it with magnesium, Mg, the percent phosphorus, and the percent oxygen, I would take 2 times 55, that's the molar mass, atomic mass of the atom manganese. And so, in this compound, with a total mass of 284, 110 grams per mole of it, for every mole of this compound, which would weigh 284 grams, 110 grams of that is manganese, which has, you know, it's a metal with some value and some unique properties. So, 284, the percent phosphorus would be equal to 2 times 31 divided by 284. And the percent oxygen would be 2 times 16 divided by 284. And if you do the math, and I did do the math and worked it out, this would be 110 divided by 284, or 30.387, or 38.7%. The phosphorus, why would I want this? If you had something like ammonium phosphate or, ammonium sulfate, and those are both two common components in fertilizers. Very frequently, out in the fields, you want to know the percent sulfur, the percent phosphorus that you're adding to your plants. If you need sulfate in your soil, usually we need nitrogen in the soil. We frequently need phosphate in the soil. So, you would do a soil analysis as well to determine the amount of phosphate present to see if you needed to boost it up. And how much do you need to boost it up? How much do you need to add? So these kinds of calculations have relevance all over the place. Besides mining and manufacturing and chemistry, agriculture, percent silver and silver nitrate or percent gold in gold ores is significant. So now my percent phosphorus would be 62 divided by 284 or 21.8%. That is your answer. And finally, the oxygen, 7 of them. I wrote 2 here, but this one is oxygen 7, so that would be 7 times 16. That would be 90, what? That would be 112 divided by 284, or 39.4% oxygen. And that's your answers for 14B. Quickly, I want to finish the rest of this. And then I'm going to post another quick video on using moles and doing these conversions and the use of a tool called the mole map. So quickly, mercury sulfide, mercury 2 sulfide. Mercury is 200, very dense, very heavy metal, 206 grams per mole. Sulfur is fairly light, non-metal, 32 grams per mole. There's 1 atom of mercury and 1 atom of sulfur in it. The entire compound, mercury 2 sulfide, has a molar mass of 200 plus 32, 200.6. So it's 232.6. So the percent mercury is equal to 200.6 divided by 232.6. And if you do the math, that comes out to a mercury composition of 86.2%, and the percent sulfur is 32 divided by 232.6, and that's equal to fractionally 0.138, but proportionally. But we're talking percent proportions, so we multiply it by 100, so that would be 13.8%. One other thing is that if you only have one element remaining to calculate, you can subtract the percentages of the other elements from 100 to get your answer. So once, this is a good example, it's only mercury and only sulfur. Once I calculate the percent mercury, everything else must be sulfur. So all I have to do is subtract the 86.2% from 100%, and that would leave me my 13.8%. So I didn't have to go through the math and do the division. I didn't even have to know the molar mass, the atomic mass of sulfur, which is 31.99, I want to say 9981, but it's very close to 32. All I had to do was, once I knew the mercury and calculated it was 86.2%, well, I needed no sulfur to know my total molecular weight, but I only had to subtract it. Now, let's do the last one and the other two problems quickly. So, the last one is calcium nitrate. The polyatomic ion nitrate, there's 2 of them. Calcium's a group 2 metal. It always has a +2 charge. The calcium has a molar mass of 40.1. Nitrogen is 14. Oxygen, once again, is 16 grams per mole. In this particular compound, there's 1 calcium. There are 2 nitrogens because I have 2 of these nitrates. And each nitrate has 1 nitrogen in it. And there's going to be 6 oxygens because in this formula, as it's given, calcium nitrate, there are 2 nitrates and each nitrate has 3 oxygens. So, my percent composition for these 3 elements in calcium nitrate are, for calcium, there's only 1 of them, so it's 40.1. And if I look at the total mass of this compound, calcium nitrate, if I add up 1 calcium at 40.1, 2 nitrogens at 14, and 6 oxygens at 16, I get a formula mass of 164 grams per mole. So I had to do that calculation first. So the calcium would be 40 divided by 164, really, I want to say 164.1, but we'll call it 164 because it won't make a big difference out beyond 3 places. The nitrogen, there's 2 of them, so that would be 28. 2 times 14 divided by 164.1. And I'm going to do the oxygen over here. The oxygen is equal to 6 times 16, which is 96, divided by 164 grams per mole. The grams per mole cancel. So we're dividing like by like, so like all percentages, it's unitless except for that percent sign. So if I do the math, the calcium ends up being 24.5%. The nitrogen is 17.1%. And of course, I can add those 2 up and subtract from 100 to get my remaining oxygen. But I'll just go ahead and do the calculation. It equals 58.5%. Okay. Number 15 asks, determine the empirical formula of a compound with the percent composition. So all we're doing is working backwards. Okay? Instead of giving you the formula and having you calculate the percentages, they're giving you the percentages and asking you to determine the formula as best we can. That's why we're saying, the empirical formula, the simplest, most formula. It's like I give you a sample of a white powder and you find out it has so much sodium and so much chloride in it, and then you work it through given the molecular weights of those 2 elements and you find out it's salt or table salt or sodium chloride. So we have this compound and it is 29.1% sodium, 40.5% sulfur, and 30.4% oxygen. Sodium is 23 grams per mole, sulfur is 32 grams per mole, and oxygen is 16. So what I'm going to do is I'm going to go through and I'm going to say 29, I'm going to assume 100 grams of substance because it's easy to work with. So 29.1 grams of sodium, because it told me if I have 100 grams of this, 29.1% of it's sodium, okay? Times 1 mole of sodium per 23 grams. It's 23 grams per mole, but it's also 1 mole per 23 grams. So I flipped my value around, my grams of sodium cancel, and I'm left with how many moles. And if I do the math, divide the 29.1 by 23, I get a little over 1. I get 1.27 mole of sodium. And then I have 40.5 grams of sulfur times 1 mole of sulfur per 32 grams of sulfur. And that, if I do the math, surprisingly gives me what? 1.27 moles of sulfur. And then the last one is oxygen. I'm going to do it up here. So I have 30.4 grams of oxygen in my 100 gram sample. And I multiply that times 1 mole of oxygen is equal to 16 grams of oxygen. Grams of oxygen cancel, and I end up with this value, which is, if I can find it here, 1.90 mole of oxygen. So I have 1.9 mole of oxygen, 1.27 mole of sodium, 1.27 mole of sulfur. What do I do with that? Well, let me tell you. You take the biggest number, 1.9, and you divide it by 1.27. And if you do the math, you'll find it equals to 1.5. So, here's my formula. This is the ratio that these compounds are in. So my formula is sodium, okay, 1.27, sodium 1, sulfur 1, and oxygen 1.5. Well, you can't have 1.5 atoms, so what do? I know my proportions, I just need them to be small whole numbers. Dalton's, kind of like going back to Dalton's law. They'll be present, or the law of multiple proportions, they'll be present in small whole number ratios. So I'm just going to double everything. So my formula is Na2S2O3, or sodium sulfite. That's your answer. That was a long way to go, I know. Finally, quickly on this last one, you have 639 kilograms of iron ore. And you have this ore that's this compound, iron 3 oxide, or Fe2O3. And the question is, how much iron am I going to get out of it? You know, I want to know what the value of this ore is. Well, iron has a molar mass of 55.8. It's not one of those that's easily roundable. Oxygen has a molar mass of 16 grams per mole. And if you look at the formula mass, Fe2O3, I take 3 oxygens, 48, and 2 irons, 111.6, and I get 159.6 grams per mole are my units. You know, all I did was add the atomic masses in the proportions according to the subscripts. Now I have 639 grams. Well, what's the percent iron? The percent iron in this compound is equal to 2 times 55.8, or like I said, 100 and, what would that be, 111.6, divided by my total mass, 159.6, and if you work it out, that's really close to 70% iron. Well, if I have 639 kilograms, I hope you can see this. I'm going to write with a different color because my orange marker is running out. I'm going to switch to blue here. So if I have 639 kilograms of this iron ore, this iron oxide, technically iron 3 oxide, and 70% of that is iron, times 70%, which of course is 0.7, or 70 divided by 100, I would get 447 kilograms of iron in 639 kilograms of the ore total. I just want to quickly do this. You now have posted, or you will by the time you see this video, a vocabulary review, a sample quiz. There's little short one-page quizzes that kind of show you the types of problems you can expect. And aren't you loving it at home now? You have your test. I took a test from the publisher for our book that itself is complete and challenging, but you have no time limit and you have no restrictions, and it's open book. So have fun with that, make a good grade on it, do it, and turn it in as soon as possible. Don't procrastinate. I'll start giving you some time limits and time estimates, especially for my seniors who are taking the concurrent credit course and need to be done by May the 7th. But we'll finish this chapter and one more, chemical reactions, and then we've really hit the bulk of first semester chemistry. I will see you in the next video over the mole map. Goodbye now.